Hi, hello. My name is Anna Peroni. So for this problem, we have that the water is pumped from the large tank shown in the diagram A below. The entrance to the pipe section is sharp-edged, meaning this is sharp-edged here. And the pipe is cast iron with a total length of 2 meters. So this is going to be like 2 meters long. Flow within the pipe is observed to be fully turbulent. For the relationship between the volumetric flow rate and actual head rise is provided in the pump specifications and is shown in diagram B. This is diagram B. Determine the volumetric flow rate for the system, show that the observation of fully turbulent flow was correct, and if the pump is 70% efficient, determine how much power must be supplied to the pump. Alright, let's do and focus on question A number first. Determine the volumetric flow rate for the system. Volumetric flow rate is typically denoted by Q, and it's equal to the velocity in the system multiplied by the area. So we don't actually know the velocity. We aren't given the velocity. But in terms of the area of the pipe, we do actually know that because they go ahead and they give us the diameter of the pipe here in the diagram. So knowing that the diameter is what it is, we can go ahead and set the area equal to pi divided by 4, 0.07, that's your diameter, squared. And that's going to give us an area quickly. Oh, whoop, I dropped my pen. Of 0.07 squared times pi divided by 4 is going to be equal to 0.003848 meters squared. Now, how do we find the velocity? It seems like kind of a big deal in order to find our volumetric flow rate, right? Well, we can go ahead and use Bernoulli's principle to solve for the velocity. And we're going to go ahead, when using Bernoulli's principle, we're going to need two reference points. We're going to place the first reference point at the very top of our tank here, that's at point 1, and the second reference point of the fluid right as it's leaving and opening up into the atmosphere at point 2. So Bernoulli's principle dictates that we have the pressure at point 1 divided by the specific weight of the fluid, plus the velocity at point 1 of the fluid divided by 2 times the gravitational constant, plus z of point 1, which is just the height, plus, and I am going to go ahead and add in the head of the pump. The head of the pump, which is going to be measured in meters. The head of the pump is kind of just like the added pressure gain that the pump is implementing into the system. Because the pump, if you think about it, it's putting energy into the fluid. It's putting energy into the fluid, and therefore it's creating more pressure from 1.1 to 0.2. So it needs to be added on to 0.1. And we're going to set that equal to all of our values at point 2, so that's going to be the pressure at point 2 divided by the specific weight of the fluid plus the velocity at point 2 squared divided by 2 times the gravitational constant plus z2, that's your height, plus the head loss. So the head loss is kind of the pressure you lose roughly because of friction, because the fluid is rubbing up against these sharp corners and the edges of the pipe, and that's going to slow it down. It's going to create a decrease in pressure, so we're going to add it on to the second part of the equation. So from here, let's go ahead and try to figure out what all these values are. Since point 1 and point 2 are both open to the atmosphere, that means P1 and P2 are going to be equal to the same pressure, in which case, and of course since this is all the same fluid, this is actually going to cancel out, and we don't have to worry about either of those terms. At point 1, since this point is at the very top layer of our tank, we can go ahead and assume that this is going to be 0, because as the fluid goes higher and higher and higher all the way up to the very top, we are assuming that it's getting slower and slower and slower all the way up until a point it stops moving at the top. So we can also get rid of z2 here. If we make our point 2 our height of 0, that means z1 is going to be equal to 6, right, because we have 6 here. But if we make point 2 equal to 0, then that's going to be z2 is equal to 0. So let's go ahead and rewrite the equation. We have z1 plus the head of the pump plus, is equal to v2 squared divided by 2g plus head loss. So let's go ahead and put some more terms into this equation. We know what z1 is, right? It's 6 meters off of our zero axis, so that's just going to be 6. The head of the pump is actually given to us in an equation, so we'll just plug that in, substitute that in. So the head of the pump is equal to plus 20 minus 2,000 q squared. And that's going to be equal to, again, v2 squared. Whoops, that doesn't look anything like a squared. v2 squared divided by 2g plus, and now head loss, there's two different types of head loss that we need to account for here. Head loss major and head loss minor. So I'm going to go ahead and write that down. The head loss major head loss, plus the head loss of the minor. And I'll go ahead and explain what those are. But first of all, let's go ahead and simplify the left-hand side of the equation. We have 26 minus 2,000. And this is going to be actually v squared a squared. I'm going to change that out. Remember, because our volumetric flow rate is equal to the velocity times the area. So we'll go ahead and put that in. Is going to be equal to, we'll keep this v2 squared divided by 2g. And when I talk about major head loss, I mostly talk about the mass, like the majority of the area that the fluid is rubbing up against that slows it down. So our equation for head loss, for major head loss, when the flow is fully turbulent, which again, they go ahead and they let us know that it's fully turbulent, which is really useful. Otherwise, you'd have to find out your Reynolds number and see if it's above or below 2,000. But since we already know it's fully turbulent, we can go ahead and assume that our Reynolds number is above 2,000, and we can use this equation. We can use the equation FL divided by D times V squared divided by 2G. And so that's going to be our equation for any major head losses we have. As for any minor head losses we have, it seems as though, what is a minor head loss? I suppose I should start with that. It's basically just any change in geometry from in the pipe system. That creates an extra amount of friction. It's not just dictated by whatever surface area is there. It can be dictated by a change of geometry or a valve or something of that such. The minor head loss we have in this system is given to us by a little hint that they tell us in the problem that the entrance to the pipe section is sharp edged. So this is going to cause us a minor head loss. So the general equation for minor head loss is going to go ahead and be equal to your coefficient of loss, k, multiplied times v squared divided by 2g. And I am going to go ahead and assume that we only have one minor head loss. We really only have to account for the sharp edges here, and we're not going to account for the head loss at the exit. I'm saying this because I think that our second point here in Bernoulli's equation is it's just at the brink. It's not outside of the pipe. It's just as the fluid is leaving the pipe. It's just been exposed to the atmosphere. So I'm going to go ahead and assume and not take into account the head loss that's going on at the exit, if there is any. So that's our new equation. Let's go ahead and simplify this even more. A squared, we already solved for A, right? We can come up and check out the top. That's going to be 0.003848. We can say squared, and multiply that times 2,000. So times 2,000 is going to give us a new number. So I'm going to come down here and say 26 minus 0.0296 v squared is equal to. Now, I've been writing this as v2, but I am going to go ahead and assume that we have steady flow in this system, meaning that the velocity is constant and is the same throughout the system. So I'm going to go ahead and just write that as v squared divided by 2g plus. Now, what is F here in this system? Well, typically what you would do is you would want to go to the Moody diagram with two numbers. You would want to go to the Moody diagram with your Reynolds number and your roughness divided by diameter number. So we don't actually need the Reynolds number in this case because we already know that this is wholly turbulent. But we do still need to find out what this number is. The roughness divided by the diameter. That's easy enough to figure out. They don't actually go ahead and tell you the roughness of this system, but they do tell you that the pipe is made out of cast iron. And you can go ahead and look this up in Table 1 of your textbook. You can see that there. Where your roughness is going to be equal to 0.00026, and of course the diameter of your pipe is just equal to 0.07, so this whole thing is going to be equal to, and I'll just 0.00026 divided by 0.07 is going to be equal to 0.003714. Okay, perfect. So now that we have that number, we don't actually need to go to the Moody diagram, because the Moody diagram, well, they give us another diagram here in the far right that it only is a function when something is wholly turbulent. It's no longer a function of the Reynolds number and the E over D number. It's just a function of the E over D number, and they've created a handy dandy little new graph that's much smaller, and that happens when you have the wholly turbulent condition. So I'm going to go ahead and find my friction coefficient F off of that diagram, and I'm going to say that it's roughly 0.0022. That's F. I'll go ahead and write that up here, 0.022. And I'm getting this off of this number and my whole completely turbulent kind of simplified Moody diagram. Now, what's L? L is just the total length of pipe that we have. That is actually just given to us in the problem statement. We'll just write down 2 meters. That's going to be 2. That doesn't look anything like a 2. That's going to be 2. Divided by, again, the diameter of the pipe, which is 0.07. And then that's going to be V squared divided by 2G. As for our minor losses, there's really no good mathematical way to calculate what K is going to be. It's usually found experimentally, so you also have to look this up in your textbook. You can find the diagram of something that looks like a sharp-edged kind of entrance or inlet for the picture, and then it goes ahead and tells you what the loss coefficient is if you have that sharp-edged condition, which for us is 0.5. So that's going to be 0.5 V squared divided by 2G. All right. So let's go ahead and continue down here. We'll rewrite this. 26 minus 0.0296 V squared is equal to, and I'm going to go ahead and take the V squared divided by 2G out of here. That's going to be 1, right? 1 for this. What's this number going to be? We have 0.022 times 2 divided by 0.07 is going to be equal to 0.6285 7 plus 0.5. We can go ahead and rewrite this once more. 0.0296 V squared is equal to, if we add those 3 numbers together, oops. I'm going to say, so plus that guy. I'm going to add those 3 numbers together, which is going to be equal to 2.1285, and divide by 2, and divide by our gravitational constant, which is 9.81. And that's going to go ahead and be equal to a 0.108489, 9, we'll say, V squared. So we'll go ahead and pull this V squared term over to the right. So we'll say 26 is going to be equal to that guy plus 0.0296. And so we have 0.138 roughly V squared. And we'll divide that on both sides, 0.138. So this is going to be 188 roughly, 0.4, which is equal to v squared. And take the rad on both sides of that. You're going to go ahead and get that your velocity of the system is equal to 13.726 meters per second. That doesn't really look like a good 13.726, so I'm going to go ahead and rewrite it. That's going to be equal to 13.726. 26, good enough. It's a 2. All right. So now that that's the velocity, and we've solved for that, we can now fairly easily solve for our volumetric flow rate, which again is just equal to the velocity of the system times the area of the pipe. So we'll go ahead and plug those numbers in. That's going to be 13.726 times our area, which we already solved for, which is up here, 0.003848, 0.003848. And we get our volumetric flow rate, which is going to be equal to 0.0528. That's going to be meters cubed per second. All right, that's part A accomplished. That is part A accomplished. So what do we have to do next here? It asks us to show that the observation of the fully turbulent flow was indeed correct. Was correct. So since we basically found our friction off of the assumption that this was wholly turbulent, let's go ahead and resolve this. We'll start with this equation that we had up here. Only this time we're not going to assume that we know what our friction coefficient F is, because we don't know if this is wholly turbulent or not. So let's go ahead and let's plug numbers in. We say, okay, 26. Let's just use the most simplified left version of this equation. So we'll say 26 minus 0.0296. So we'll say 26 minus 0.0296 v squared is equal to, and now the right-hand side of our equation, which is going to be equal to v squared divided by 2g, v squared divided by 2g, plus, we'll leave f in. We'll say f is going to be times 2 divided by 0.07. So f, because we don't know what f is, because we don't know if this is turbulent or laminar. We do know still the length, though, and we still do know the diameter, though. Times, obviously, v squared divided by 2g. And lastly but not leastly, the k should still be the same, so we'll add in 0.5 v squared divided by 2g plus 0.5 v squared divided by 2g. That is a v. Okay. So this is our new equation. I'm just going to double check that everything looks good. I kind of skipped a couple steps in the creation of this, but basically this is exactly what we did the last time, kind of putting together Bernoulli's equation, only this time we are not assuming that we know what F is, because we are not assuming that this is wholly turbulent. So we'll go ahead and try to solve for this equation once again. Let's go ahead and pull out the v squared divided by 2g. 6 v squared is equal to v squared divided by 2g. This is going to be 1 plus, now 2 divided by 0.07 is going to be equal to 28.57 f. 28.57 f. F. I'll just rewrite that. That is capital F. Okay. Plus 0.5. And we can go ahead and rewrite this again. 0.0296 v squared is equal to, yeah, we can say v squared divided by 2g, 1.5 plus 28.57 f. Scrolling down. Now I I am just going to put these back in, I think. I'm just going to put these back in. Kind of convoluted way to do this, I'm sorry. But I'm going to take 1.5 divided by 2 and divided by 9.81, which is G. It's going to give me a 0.07645, 0.07645 V squared plus, now I'm going to take 28.57, which is the coefficient of F right there, divided by 2 and divided by 9.81, and that's going to go ahead and leave me with 1.456, 1.456 V squared F, or F V squared. And I'm going to leave 26 over here and scooch this coefficient onto the other side. We're going to say 0.07645 V squared plus 1.456. Oops. I accidentally changed my color to white. Sorry about that. 1.456 FV squared. And we're going to add this onto the other side, 0.0296 V squared. And I'm going to take all the V squares out of these three terms, and we're going to say 26 is equal to V squared, which is equal, V squared times 0.07645 plus 1.456 F plus 0.0296, and we can simplify that even more, putting V squared on this side of the equation, and we're going to have 26 divided by, and we'll just add these two together, so it's going to be 0.07645 plus 0.0296. So that's going to be equal to 0.106. 5 plus 1.456 F. And that's going to be solving for V. And as you can see, we still have our one variable in here, even though we've solved for V successfully. It's still equal to kind of an unknown value. So what do we do to solve for this? Well, you're going to need another equation also that has V and F in it. And so we can have two equations with two unknowns and substitute one to the other. Where do we find such an equation, you ask? Well, typically, when we find the friction force, we go to the Moody diagram. The Moody diagram, which was kind of discovered experimentally, has a following equation that is valid for most of the range of the Moody diagram, and it's on the very back page. It's just on the flip side of the page of the Moody diagram, and it's given to us as Colebrook's equation. And Colebrook's equation is given as this. It's going to be 1 divided by the rad of F, which is equal to negative 2.0 log of, that's going to be the roughness divided by the diameter, divided by 3.7 plus 2.51 divided by our Reynolds number, rad F. And we would actually know how to reduce this just in terms of F and V. We would. All we have to do is we can say, okay, negative 2 log. We already know what E over D is. We already solved for that, remember? Because it's just the roughness of the cast iron divided by the diameter of the pipe. It's just going to be equal to 0.003714. So we'll go ahead and plug that in. 0.003714 divided by 3.7 plus 2.51 plus 2.51 divided by, now what's the Reynolds number? The Reynolds number is just going to be equal to the density of your fluid multiplied by the velocity, right? It's going to be the density of your fluid multiplied by the diameter times the velocity divided by mu, right? That's your Reynolds number. Yeah, that's your Reynolds number. I can't believe I drew a blank on that a little bit. So, knowing that that's what that is, as you can see, we actually do know the density, we do know the diameter, we do know the viscosity. So, knowing that the density is going to be equal to 1,000, and that our diameter is equal to 0.07, and that our dynamic viscosity is equal to 1.12 times e to the negative 3, we can go ahead and simplify this even more and say that you're going to have negative 2 log, blah, blah, blah. So let's go ahead and divide that, might as well. So we have 0.003714 divided by 3.7. That's going to be equal to basically 0.001 plus, and we're going to have 2.51 divided by 1,000 divided by 0.07 and multiplied by 1.12 e to the 3 negative. And so that's going to be equal to 0.000040116 v to the negative 1. And there you go. You have two equations with two unknowns, v and f. And if you solve for these two equations by plugging v, this guy, into here, you can go ahead and find what f is for real and what v is for real. And you're going to come up with the same number. Doing this is a little long on a calculator, but you can do it. And ultimately, you're going to come up with the same, if not a very similar answer to what you got in the first place. So you're going to get f is going to be equal to 0.022. Okay. But does that prove that this is fully turbulent? Does that prove that this is fully turbulent? Well, if we get f is equal to 0.022, and our velocity is going to be roughly the same, it's going to be roughly 13 meters per second. To determine whether or not a flow is turbulent or laminar, your Reynolds number has to be below or above 2,000. If your Reynolds number is less than 2,000, then that's going to be a laminar flow. And if your Reynolds number is above 2,000, then that's going to be a turbulent flow. Turbulent flow. Laminar is when everything's going straight and easy. Turbulence when everything's bouncing around because it's going so fast, the fluid's going so fast. So our Reynolds number, remember we already gave the equation up here, is going to be rho dv divided by your dynamic viscosity, rho dv divided by your dynamic viscosity, and that's going to be equal to 1,000 multiplied by the diameter of the pipe, multiplied by v, which you have gotten from substituting these two equations into one another. That's going to be equal to 13 meters, and divided by mu, and whoops, mu, it has an actual value. It's going to be 1.12 e to the negative 3. You can look that up in your textbook. And I can go ahead and plug those numbers in, though right off the way I can probably tell you this is going to be above 2,000. Yeah, this is going to give you roughly a Reynolds number of 812500, which is much bigger than 2,000. So we can rest assured knowing that this is wholly turbulent. So that's part B. Let's go ahead and take a look at part C. If the pump is 70% efficient, determine how much power must be supplied to the pump. Okay, so when we talk about efficiency, we're talking about how much power gets put into the fluid divided by how much power it takes to operate the pump. So if our efficiency is 70% or 0.7, and the power of the fluid can be represented by the equation rho g q h p as in the head of the pump, the actual head of the pump, divided by the power it takes to run the pump, which is what we're actually trying to find, we can find this variable fairly quickly here. All we have to do is plug our numbers in once again. So we say 0.7 is equal to the density of our fluid, which is going to be 1,000 kg divided by meters cubed, times g, which are gravitational constant, 9.81, times meters per second squared, multiplied by q, which we already solved for, right? Q, which we already solved for, which is going to be 0.0528. 0.0528. Yeah, meters cubed per second. Multiplied times the head of the pump, which again is just given to us by the equation 20 minus 2,000 q squared. So we'll say 20 minus 2,000 q, since I'm running out of space, I'm just going to say q squared. And that's the top of our equation. This is pow p. I'm going to go ahead and simplify. Again, just knowing that q is going to be equal to 0.0528. Okay, say 0.0528 squared multiplied by 2,000. It's going to be equal to 5.57 roughly. Wait, did I get that right? 0.0528 squared times 2,000. Yeah, it's going to be equal to 5.57 roughly. And that's going to be a negative 5.57. Added on to 20 is going to be 14.42 multiplied by 0.0528 once again, multiplied by 9.81, and then multiplied by 1,000 is going to go ahead and give you 7471.336 watts. That's how much power is going into the fluid over pow p. We can readjust this so that our power of the pump is going to be equal to, divided by 0.7, is going to be equal to 10,673.33 watts. And we'll go ahead and simplify that a little bit more, and we'll say that it takes about 10.67 kilowatts to operate the pump. And that is part C. And that is all parts of the problem. So there you go. There you have it. Yeah, we're good to go.